Section 27 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynda Marie Neilson, Vancouver, BC. The Theory and Practice of Brewing by Michael COMBRUNE. Section 27. Of the proportion of cold water to be added to that which is on the point of boiling, in order to obtain the desired heat in the extract. The degree of heat which causes water to boil is determined by Fahrenheit scale to 212. It is in our power to give to any part of the extracting water this degree of heat, and by adding to it a sufficient proportion of water of an equal heat with that of the air, and blending these two quantities with the grist, to bring the whole to the required temperature. The rules for obtaining this end are extremely simple, and cannot be unknown to those who are skilled in arithmetic operations. But as our view is to render this part of our work generally useful, we think it will be proper briefly to lay down these rules and to illustrate them by the examples of our two brewings. Rule to ascertain the heat of the first mash. Let A express the degree of boiling water, B the actual heat of the air, C the required degree for the extract, M the whole quantity of water to be used, N the volume of the malt, X that part of the water which is to be made to boil, will be determined by the following equation. X equals C minus B times M plus N divided by A minus B. The quantity of water used added to the volume of the grist. Their sum, Z, multiplied by the heat required less the heat of air. This produce divided by the heat of boiling water, 212, less the heat of the air will quote how much is to be made to boil or brought through 212. That is how high the copper is to be charged. The remainder of the length of the whole liquor for this mash is the quantity to be cooled in. The first example is that of a brewing of small beer, when the heat of the air is at 60. See page 232. The volume of the 6/4 of malt was estimated at 3.42 barrels. See page 268. The first liquor is 14.5 barrels. See page 247. And the heat required for the first mash 154 degrees. See page 247. First mash. M equals 14.50 barrels of water. N equals 3.42 volume of grist. M plus N equals 17.92. C 154 heat of the first mash. B equals 60 heat of the air. C minus B equals 94. A heat of boiling water, 212. B heat of the air, 60. 168,448 divided by A minus B, 152, equals 1108 barrels of water to be made to boil out of the 14.5 barrels which are allocated for the first mash. The incidents to be mentioned are not considered in this calculation. The next example of a brewing is that of a grist of 11 quarters of malt for porter or brown beer. The medium heat of the air is 40 degrees. The volume of the grist, 6.32 barrels. See page 268. The first liquor to mash with 16 barrels. See page 245. And the heat expected in the mash, 157.5 degrees. See page 245. First mash of brown strong beer. 16 barrels of water. 6.32 volume of malt. 157 heat required in the mash. VD page 247. 40 heat of the air. Heat of boiling water 212 equals 261,144 divided by 172 equals 15.18 barrels of water to be made to boil out of the 16 barrels. I will give one proof of the certainty of this rule by setting down the state of this first mash from it. A. 3,218.16 number of degrees of heat in 14.66 barrels of boiling water. 16 barrels of water to first mash. 15.18 barrels made to boil. 0.82 barrels to cool in. 40 heat of cold water. B. 32.80 number of degrees of heat in 1.34 barrels of cold water. 15.18 barrels of boiling water. 0.82 cold water. 6.32 volume of grist. C. 22.32 barrels volume of the whole mash. 6.32 barrels volume of the 11 quarters of malt. 0.4 heat of the grist. 252.80 number of degrees of heat in the grist. 32.80 B. 3218.16 A. C. 350,376 divided by 22.32 equals 157 degrees of heat required in the first mash, as above. So long as the mixture consists only of two quantities of different heat, as is always the case of the first mash, the preceding solution takes place. But in the second and other mashes where three bodies are concerned, each of different heat, viz. The boiling water, the cold water, and the mash, are to be mixed and brought to a determinate degree, the rule must be different. Yet, like the former, it is the same with what is used in similar cases of allying, when different metals are to be melted down into a compound of a certain standard, or different ingredients of different value to be blended in order to make a mixture of a determinate price. What the different density of the metals or the different value of the ingredients are, in these cases, the different degrees of heat of the boiling water, the grist, and the air are in this rule to ascertain the heat of the second mash and of the subsequent ones. Let the same letters stand for the things they signified before, and D express the actual heat of the grist. Then will X equals C minus B times M plus C minus D times N over A minus B. Or in plain terms, the heat required less the heat of the air multiplied by the quantity of water used. The heat required less the heat of the goods multiplied by the volume of the goods. Their sum divided by the heat of the boiling water, 212, less the heat of the air, will quote the quantity to be made to boil or to be brought through 212. The remainder part of the whole liquor for the mash is consequently the quantity to be cooled in. We may now collect the circumstances of the two brewings, and find the quantity of boiling water required for their second and subsequent mashes exclusively of the incidents which will hereafter be mentioned. The first mash for the 6 quarters of small beer had 154 degrees of heat, but this and every mash loses, in the time the extract is parting from it, 4 degrees, which reduces the heat to 150 degrees. The volume of this grist in its dry state was 3.42 barrels, but now, by being expanded and having imbibed much water, it occupies 3 times that space, or 10.26 barrels. The air is supposed to continue in the same state of 60 degrees of heat. The length and heat to be given to the 3 remaining mashes are as follows. See page 247. Degrees of heat: 154, 166, 170, 174. Barrels of water: 14 and a half, 14 and a half, 11, 11. Liqueurs: first, second day combined to 1 wort, third day and fourth day combined to the second wort. Second mash for small beer. C equals 166 heat required in the mash. D equals 150 heat of the goods. C minus D equals 16. N equals 1026 volume of the goods. C minus D times N equals 16,416. C equals 166 heat required in the mash. B equals 60 heat of the air. C minus B equals 106. M equals 1,450 barrels of water. C minus B times M equals 153,700. C minus D times N equals 16,416. A equals 212 and B equals 60. Therefore, 170,116 divided by A minus B, 152, equals 11.19 barrels of water to be made to boil out the quantity allotted for the second mash. Third mash: 170 heat of the third mash, 60 heat of air, 162 heat of goods, 1,100 barrels of water, third mash, 1,026 volume of grist, 129,208 divided by 152, 8.50 barrels to be made to boil out of the quantity of water allowed for the third mash. Fourth mash: 174 heat of the fourth mash, 60 heat of air, 166 heat of goods. 11 barrels of water for fourth mash, 1,026 volume of goods. 133,608 divided by 152 equals 879 barrels to be made to boil out of the quantity of water allowed for the fourth mash. The liquors of this brewing of common small beer, when the mean heat of air is 60 degrees, must therefore be ordered in the following manner, the incidents hereafter to be noticed, excepted. Lengths of liquor. 1 liquor, 14.5. 2 liquor, 14.5. 3 liquor, 11. 4 liquor, 11. Boiling water, barrels. 1 liquor, 11. 2 liquor, 11.5. 3 liquor, 8.5. 4 liquor, 8.75. Cold water, barrels. 1 liquor, 3.5. 2 liquor, 3.25. 3 liquor, 2.5. 4 liquor, 2.25. Total, 1 liquor, 14.5. 2 liquor, 14.25. 3 liquor, 11. 4 liquor, 11. The heat of the first mash for the 11 quarters of brown beer was 157 degrees. See page 245. And after the parting of the extract from it, 153, the volume of the grist in its dry state was valued at 6.32 barrels of water. See page 268. But for the reasons before mentioned, it now occupies 3 times that space, or 18.96 barrels. The air is supposed to continue at 40 degrees, and the length of heat to be given to the different mashes were determined as follows. See page 245. Degree of heat: 157, 158, 162, 164, 165. Barrels of water: 16, 8, 12, 9, 9. Liqueurs: first, second, third, fourth, fifth. First and second make up the first wort. Third makes up the second wort. Fourth and fifth make up the third wort. Second mash of porter or brown strong. 212 boiling water, 40 degrees heat of air equals 72. 158 heat of second mash. 158 heat of the grist or goods. 1896 volume of goods. 8 barrels of water. 103,880 divided by 172 equals 6.03 barrels of water to be made to boil for the second mash. Third mash: 212 heat of boiling water, 40 heat of air equals 172 heat of air. 162 heat of third mash. 154 heat of goods. 12 barrels of water. 161,568 divided by 172 equals 9.45 barrels of water to be made to boil for third mash. Fourth mash: 164 heat of fourth mash. 158 heat of goods. 18.96 volume of grist wetted. 9 barrels of water. Totals 122,976 divided by 172 equals 7.14 barrels of water to be made to boil for the fourth mash. Fifth mash: 165 heat of fifth mash, 160 heat of goods, 40 heat of air, 9 barrels of water. 123,980 divided by 172 equals 7.20 barrels of water to be made to boil for the fifth mash. The liqueurs of this brewing of brown beer must therefore be ordered in the following manner: barrels of boiling water, 15 1/4, 6, 9 1/2, 7, 7. Barrels of cold water, 3/4, 2, 2 1/2, 2, 2. Totals for the liqueurs: 16 for the first, 8 for the second, 12 for the third, 9 for the fourth, and 9 for the fifth. What in the brewery is generally called cooling in must be settled for this brewing according to the number of barrels of cold water specified as above, the incidents hereafter to be noticed excepted. Each of these calculations may be proved in the same manner as was done before. This method of discovering the proportion of water to be cooled in deserves, on account of its plainness and utility, to be preferred to any other, which depend only upon the uncertain determination of our senses. End of section 27. Recording by Lynda Marie Neilson, Vancouver, BC.
Section 28 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 28. Of Mashing. Of late years, great progress has been made towards perfecting the construction and disposition of brewhouse utensils, which seem to admit of very little further improvement. The great copper, in which the waters for 2 of the extracts receive their temperature, is built very near the mash tun, so that the liquid may readily be conveyed to the ground malt without losing any considerable heat. A cock is placed at the bottom of the copper, which being opened lets the water have its course through a trunk to the real bottom of the mash tun. It soon fills the vacant space, forces itself a passage through many holes made in a false bottom which supports the grist, and, as the water increases in quantity, it buoys up the whole body of the corn. In order to blend together the water and the malt, rakes are first employed. By their horizontal motion, less violent than that of mashing, the finest parts of the flour are wetted and prevented from being scattered about or lost in the air. But as a more intimate penetration and mixture are necessary, oars are afterwards made use of. They move nearly perpendicularly, and by their beating or mashing, the grains of malt are bruised, and a thorough imbibition of the water procured. The time employed in this operation cannot be settled with absolute precision. It ought to be continued till the malt is sufficiently incorporated with the water, but not so long as till the heat necessary to the grist be lessened. As bodies cool more or less speedily, in proportion to their volume and the cohesion of their parts, a mash which has but little water, commonly called a stiff mash, requires a longer mashing to be sufficiently divided, and from its tenacity is less liable to lose its heat. This accounts for the general rule that the first mash ought always to be the longest. After mashing, the malt and water are suffered to stand together unmoved, generally for a space of time equal to that they were mashed in. Was the extract drawn from the grain as soon as the mashing is over, many of the particles of the malt would be brought away undissolved, and the liquor be turbid, though not rich. But by leaving it some time in contact with the grain, without any external motion, many advantages are gained. The different parts of the extract acquire a uniform heat. The heaviest and most terrestrial subside, the pores being opened by heat, imbibe more readily the water, and give way to the attenuation and dissolution of the oils. When the tap comes to be set, the extract to be drawn from the grist, as the bottom of the mash has become more compact, the liquor is a longer time in its passage through it, is in a manner strained, and consequently extracts more strength from the malt, and becomes more homogeneous and transparent. Such are the reasons why the grist should not only be mashed pretty long, but likewise be suffered to rest in equal time. It is the practice of most brewers, as experience shows it best, to rake the first mash half an hour, to mash it 1 hour more, and to suffer it stand 1 hour and a half. The next extract is commonly mashed 3/4 of an hour, and stands the same space of time. The third, and all that follows, are allowed 1/2 hour each, both for mashing and for standing. The heat of the grist being in this manner equally spread, and the infusion having received all the strength from the malt, which such a heat could give it, after every mashing and standing, is let out of the tun. This undoubtedly is the fittest time to observe whether our expectations have been answered. The thermometer is the only instrument proper for this purpose, and ought to be placed or held where the tap is set, adjoining to the mouth of the under back cock. The observation is best made when the extract is run nearly half, and as by it we are to judge with what success the process is carried on. It is necessary to examine every incident, which may cause a deviation from the calculated heat. End of section 28.
Section 29 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Chris Gray, CG Systems and Gadgets. The Theory and Practice of Brewing by Michael COMBRUNE. Section 29. Of the incidents which cause the heat of the extract to vary from the calculation, the allowances they require, and the means to obviate their effects. By incidents, I understand such causes as affect either the malt, the water, or the mash during the time the brewing is carrying on, so as to occasion their heat to differ from what is determined by calculation. As these might frequently be a reason of disappointment, an inquiry into their number and effects will not only furnish means to prevent and rectify the errors they occasion, but also serve to confirm this practice. In our researches on the volume of malt, some notice was taken of the increase of bodies by heat and the loss occasioned by evaporation. Water, when on the point of ebullition, occupies the largest space it is susceptible of, but contracting again when cold water is added to it. The true volume of both, when mixed together, remains uncertain, and may cause a difference between the calculated and real degree of heat. This cause, however, producing an effect opposite to, and balanced in part by evaporation, becomes so inconsiderable as hardly to deserve any further consideration. Water, just on the point of ebullition, may be esteemed heated to 212 degrees, though, by the continuation of the fire, or by any other cause, the heat never goes beyond this. Yet was cold water added to that, which violently boils, the degree expected from the mixture would be exceeded, for the cold water absorbing the superfluous quantity of fire, which otherwise flies off, becomes hot itself, and frustrates the intent. The time, therefore, of adding the cold water to the hot is immediately before the ebullition begins, or when it is just ended, and in proportion as we deviate from this practice, the heat in the extract will differ from the calculated degree. The water for every mash should, as near as possible, be got ready to boil, and be cooled in just before it is to be used. A liquor which remains a long time after the ebullition is over, and the fire has been damped up, loses part of its heat. If cold water is applied to it, the effect cannot be the same as it would have been at first. On the contrary, if the liquor is got ready too soon, and cold water immediately added to it, in order to gain the proper degree of temperature, by leaving the mixture long enough, though the fire is stopped up, more heat than necessary will be received from the copper and brickwork, especially if the utensils are large. In both cases, the degree in the extract will not answer the intent. The effect of effervescence next deserves our consideration, but this takes place only when the water first comes in contact with the malt. Germinated grains must, to become malt, be dried so that their particles are made to recede from one another, thus deprived of the parts to which their union was due when they come in contact with other bodies. As water, they strongly attract the unitive particles they want, and excite an intestine motion which generates heat. This motion and this heat are more active in proportion as the grain has more strongly been impressed by fire and the extracting water is hotter. A large quantity of liquor applied to the grist is less heated than a small one by the power of effervescence. The least quantity of water necessary to shew that power must be just so much as the malt requires to be saturated, which we have seen to be double the volume of the grain. When more water than this is applied to the grist, the real effervescing heat is by so much lessened, being dispersed in more than a sufficient space. A table shewing the heat of effervescence for every degree of dryness in the malt can only be formed from observations. To apply this table to practice, and to find out, for any quantity of water used in the first mash, the degrees of heat produced by effervescence, 3 times the volume of the grist must be multiplied by the number expressing the effervescing heat of malt of such a degree of dryness, and this produce be divided by the real volume of the whole mash. A table shewing the heat occasioned by the effervescing of malt for its several degrees of dryness. Dryness of malt 119 degrees, heat of effervescence 0. 124 degrees 3.5, 129 degrees 7, 134 degrees 10.5, 138 degrees 14, 143 degrees 17.5, 148 degrees 21, 152 degrees 24.5, 157 degrees 28, 162 degrees 31, 167 degrees 35, 171 degrees 38.5, 176 degrees 40. Malt dried only to 119 degrees raises no effervescence, and the strongest is generated by malt dried to 176 degrees. The heat produced by this amounts to 40 degrees, but the number of effervescing degrees in this or any other case are reached but from success attending our endeavours, ultimately to penetrate the malt by heated water, or not until the grist is perfectly saturated, which, in point of time, generally takes up the whole space of the first mashing and standing. The air, therefore, cannot cause any diminution of heat, an incident which affects considerably every subsequent mash. The little copper being more distant from the mash tun than the other, the water there prepared, in its passage to the goods, loses some part of its heat, and in proportion to the quantity of water used, to the number of the extracts that have been made, and according as the mashes have more or less consistency, in the same time do they part with more or less of their heat. Observations made separately upon strong and small beer have shewn the proportions of this loss to be as follows. For strong beer, mashes 2D, 3D, 4th, 5th. Heat lost 8 degrees, 12 degrees, 8 degrees, 8 degrees. For small beer, mashes 2D, 3D, 4th. Heat lost 8 degrees, 16 degrees, 20 degrees. A grist not perfectly malted, or one which contains many hard corns, disappoints the expectation of the computed degree, as the volume cannot be such as was estimated from an equal dryness of true germinated grain. It has been observed that, in perfect malt, the shoot is very near pressing through the exterior skin. By so much as it is deficient in this particular, must it be accounted only as dried barley or hard corn. I know no better way of judging what proportion of the corn is hard to what is malted than by putting some in water, the grains not sufficiently grown will sink to the bottom. Were this to be done in a glass cylinder, the proportion between the hard and malted corn might be found with exactness, the unmalted parts being estimated with regard to their volume as barley. A quarter of them will be to the barrel of water as 1:56 to 1. Supposing, therefore, that in the brown beer grist before mentioned, the proportion of hard corns is of 2 quarters out of 11, to discover the true volume of such a grist, the following rule may be used. 2 quarters of hard malt, 9 quarters of true malt, 1:56 volume of 174 volume at 130 degrees of dryness, 1 quarter, 3:12, 1566, 3:12 volume of 2 quarters of hard corn, total number 11, 1878, 172 volume of 1 quarter of this malt to 1 barrel of water, and consequently the 11 quarters will fill a space equal to that of 647 barrels. By means of this rule, we may find what increase of heat any proportion of hard corns will occasion, as will be seen in the following table. Proportions of hard corns: a quarter, a sixth, an eighth, a 16th, a 32nd of the grist. Greater heat of the mash: 4 degrees, 3, 2, 1, a half degrees. But the brewing of such malt ought to be avoided as much as possible, as the hard parts afford no strength to the extract. If a grist is not well and thoroughly mashed, the heat not being uniformly distributed in the different parts of the extract, the liquor of the thermometer, when placed in the running stream of the tap, will fluctuate and, at different times, shew different degrees of heat. In this case, the best way is to take the mean of several observations, and to estimate that to be the true heat of the mash. If the gauges of the coppers are not exactly taken, a variation must be expected. Though the small and hourly variations in the state of the atmosphere have but little influence upon our numbers, a difference will be observed in any considerable and sudden changes either of the heat or of the weight of the air. Our instruments, and in particular the thermometer, are supposed to be well constructed and graduated. If the water cooled in with is more or less hot than estimated, or if the time of mashing or standing is either more or less than was allowed for, the computation must be found to vary from the event. While the malt is new, if the fire it has received from the kiln has not sufficiently spent itself, this additional heat is not easily accounted for. This is likewise the case when malt is laid against a hot brickwork of coppers, and on the contrary, a loss of dryness may be occasioned if the storerooms are damp. The artist should be attentive to all these incidents, that not pointing them out might appear neglectful. Enumerating more would exceed the bounds of use. Small grists brewed in large utensils lose their heat more readily by laying thin and greatly exposed to the air, and, on the contrary, a less allowance for the loss of heat is required in large grists, and to which the utensils are in proportion. This really is the only difference between brewings carried on in large public brewhouses and those made in small private places, in other respects constructed upon the same plan and with an equal care. Prejudice has propagated an idea that where the grists are large and the utensils in proportion, stronger extracts could be forced from the malt in proportion to the quantity, and that more delicate beers could be made in smaller vessels less frequently used. These assertions, from what has been said, will, I hope, need no further inquiry. The degrees of heat for the extracts are fixed for every intent, and it cannot be advantageous by any means to deviate from them. Brewings will most probably succeed in all places where the grist is not so large as to exceed the bounds of man's labour, and not so small as to prevent the heat from being uniformly maintained. The disadvantages are great on all sides when a due proportion is not observed between the utensils and the works carried on. It will now be proper to continue the delineation of our two brewings and to put all the circumstances relating to them under one point of view. A brewing for porter or brown strong beer, computed for 40 degrees of heat in the air. 11 quarters of malt, dried to 130 degrees. 132 pounds of hops for 27 barrels a half, to go out at 3 Worts, 31 inches above brass. Volume of grist, 632. Water for first mash, 16 naught. 2232. 632 volume of grist. 3 1896. 6 effervescing degrees. 3 degrees for hard corns. 9 degrees equal to 2 inches a quarter, less cooling in for the first mash. 7 effervescence per table. 2232. 132.72. 6 degrees of heat gained in the first mash by effervescence. 13,392. Mashes: first, 2D, 3D, fourth, fifth. Degrees of heat: 157, 158, 162, 164, 165. Barrels of water used: 16, 8, 12, 9, 9. Quantity cooled in by calculation: 3 quarters, 2, 2.5, 2, 2. Boiling water by calculation: barrels: 15 1/4, 6, 9.5, 7, 7. Allowances for incidents: GC, LC, 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 less 2 inches, quarter, more 2 inches, more 3 inches, more 2 inches. A brewing for common small beer, computed for 60 degrees of heat in the air. 6 quarters of malt dried to 130 degrees, 36 pounds of hops, 30 barrels 3 quarters, to go out 56 inches above brass. Grist, 342, water, 1450, 1792. Volume of grist, 342, 3, 1026. 7 effervescing degree for malt at 130. 4 degrees for effervescence, 1 degree for hard corns, 3 degrees for new malt hot. 8 degrees to be deduced from the first cooling in. 1792, 7182, 7168. 14. 4 degrees of heat gained in the mash by effervescence. Mashes: first, 2D, 3D, fourth. Degrees of heat: 154, 166, 170, 174. Whole quantity of water used: barrels: 14.5, 14.5, 11, 11. Quantity to be cooled in: barrels: 3.5, 3.25, 2.5, 2.25. Boiling in by calculation: charged barrels: 11, 11.25, 8.5, 8.75. Allowances for incidents: GC, GC, LC, LC, inches, less 2, more 2, more 4, more 5. These computations, perhaps, will appear more troublesome than they really are, but besides the facility which exercise always gives for operations of this kind, the satisfaction of proceeding upon known principles will, I hope, encourage the practitioner to prefer certitude to doubt. One advantage must greatly recommend it, and at the same time secure the uniformity of our malt liquors. Tables for each sort and season may be made beforehand, and will serve as often as the circumstances are the same. The trouble of the computations will by that means be saved, and by collecting together different brewings of the same kind, the artist will, at any time, have it in his power to see what effect the least deviation from his rules had upon his operations, and to what degree of precision he may hope to arrive. That nothing may be wanting in this work to facilitate the intelligence thereof, I shall insert the method of keeping the account of actual brewings made according to the computations I have here successively traced down. The first column contains the charges of the coppers and the numbers computed. The next, the brewings made from these numbers, with their dates, and the degrees of heat found by observation. The variations occasioned by unforeseen incidents are supposed to be allowed for, at cooling in, by the artist, upon the principle that each inch of cooling in answers to 4 degrees of heat. Noting in this manner the elements of every brewing we make, when the drink comes into a fit state for use, we are enabled to compare our practice with the principles which directed it. By this means, experiments constantly before our eyes will be the most certain and the best foundation for improvement. Small beer, heat of air 60 degrees, 6 quarters of malt, 36 pounds of hops, for 30 barrels 3 quarters, to go out 56 inches above brass. Observations: 1760 June 27th, 1760 June 30th, 1760 August 3rd, 1761 July 3rd, 1761 July 3rd. First liquor, charge great copper 2 inches a half above brass, cool in to 13 inches a half above brass, rake half hour, mash 1 hour, stand 1 hour half, heat of the extract intended 150 degrees, 151, 149, 150, 153, 150. 2D liquor, charge great copper 7 inches above brass, cool in to 13 inches a half above brass, mash 3 quarters hour, stand 3 quarters hour, heat intended 162 degrees. 1 wort came in 33 inches above brass, boiled 1 hour half, went out 28 inches above brass, into 13 inches a half above brass. 161, 163, 163, 148, 162. Third liquor, charge little copper 3 inches a half above brass, cool in to 13 inches above brass, mash half hour, stand half hour, heat expected 166, 2, 166, 165, 165, 167, 15. 4D liquor, charge little copper 10 inches a half above brass, cool in to 13 inches above brass, mash half hour, stand half hour, heat expected 170 degrees. 2 wort came in 39 inches above brass, boil down to 28 inches above brass. 166, 165, 165, 167, 15. Length 31 barrels. Porter, heat of the air 40 degrees, 11 quarters of malt, 132 pounds of hops for 27 barrels half, to go out at 3 worts, 31 inches above brass. 1761, November 20th, 43 degrees. 1761, November 3rd, 35 degrees. 1761, November 3rd, 40 degrees. First liquor, charge great copper 13 inches above brass, cool into 17 inches half above brass, rake half hour, mash 1 hour, stand 1 hour half, extract expected 153 degrees, 153, 151, 154. 2D liquor, charge little copper 2 inches a half below brass, cool into 3 inches above brass, Mash 3/4 hour. Stand 3/4 hour. Heat expected at the tap 154 degrees. 1 wort came in, great copper 16 inches above brass. Boiled 1 hour. Went out 13 inches above brass. 155, 157, 153. 3D liquor. Charge little copper 10 inches above brass. Cool in to 16 inches above brass. Mash half hour. Stand half hour. The tap to come down 158 degrees. 2 wort came in, great copper 11 inches above brass. Boiled 2 hours. Went out 5 inches above brass. 157, 157, 158. 4th liquor. Charge little copper 1 inch and a half above brass. Cool into 6 inches a quarter above brass. Mash half hour. Stand half hour to come down 160 degrees. 161, 160, 161. 5th liquor. Charge little copper 1 inch and a half above brass. Cool into 6 inches a quarter above brass. Mash half hour. Stand half hour. Tap to come down at 161 degrees. 3 wort came in 25 inches above brass. Went out 13 inches above brass. 160, 161, 160. End of section 29.
Section 30 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 30 of the disposition of the worts when turned out of the copper. The thickness they should be laid at in the backs to cool, and the heat they should retain for fermentation, under the several circumstances. When a process of brewing is regularly carried on with 2 coppers, the worts come in course to boil, as the extracts which form them are produced. It would be tedious and unnecessary to describe the minutest parts of the practice, which, in some small degree, varies as brewing offices are differently constructed, or the utensils are differently arranged. Without the assistance of a brew house, it is perhaps impossible to convey to the imagination the entire application of the rules before laid down, but with one, I hope they need little, if any, farther explanation. The worts, when boiled, are musts possessing an intended proportion of all the fermentable principles, except air. This was expelled by fire, and until their too great heat is removed, cannot be administered to them. In musts, which spontaneously ferment, the external air excites in their oils an agitation, which, heating and opening the pores of the liquor, expands and puts in action the internal air they possess. The case is not exactly the same with regard to those musts which require ferments. The air wanted in boiled worts must be supplied by the means of yeast. Was the heat of the wort such as to occasion the immediate bursting of all the air bubbles contained in the yeast, an effervescence rather than a fermentation would ensue. Now a heat superior to 80 degrees has this effect, and is therefore one of the boundaries in artificial fermentation. 40 degrees of heat, for want of being sufficient to free the air enclosed in the yeast bubbles, and to excite their action, is the other. Within these limits must the wort be cooled to, and the precise degree, which varies according to the different circumstances they are in, and to the intent they are to be applied to, is, together with the means of procuring this heat, the purport of this section. Worts, when in the copper, boil at a heat somewhat superior to that of 212 degrees. The more this is exceeded, the stronger the liquor is. The instant the wort is suffered to go out of the copper, it loses more heat than in any other equal space of time after it has been exposed to the air. In the course of the natural day, or in 24 hours, the heat of the air varies sometimes, especially in summer, as much as 20 degrees. If the wort, after having reached the lowest heat in this interval, was suffered to remain in the coolers, till the return of a greater in the air, it would be influenced by this increase, expand, and be put in action, and, should there be at this time any elastic air in any part of the coolers, which sometimes happens, either from the sediment of former worts, from the backs not being clean swept, or from the wood being old and spongy, the wort supposed to be left to cool, will, by receiving the additional heat from the air, and blending with the incidental elastic air adhering to the coolers, bring on, in a lower degree, the act of fermentation, an accident by the artist called the backs being set. For this reason, a wort should never be suffered to lay so long as to be exposed to the hazard of this injury, which generally may happen in somewhat more than 12 hours. Thus we are directed to spread or lay our worts so thin in the backs, as they may come to their due temperature within this space. In summer it is sufficient if the backs be covered. In winter a depth of 2 inches may oftentimes be allowed with safety. From the inclination of the coolers or backs to the place where the worts run off, from their largeness, or from the wind and air warping them, a wort seldom, perhaps never, lays everywhere at an equal depth, and cannot therefore become uniformly cold in the same space of time. This renders the use of the thermometer difficult, though not impracticable. To supply the want of this instrument with some degree of certainty, the hand intended to feel the worts is brought to the heat of the body, by placing it in the bosom, until it has fully received it. Then dipping the fingers into the liquor, we judge, by the sensation it occasions, whether it is come to a proper degree of coolness to be fermented. As the external parts of our bodies are generally of about 90 degrees of heat, some degree of cold must be felt before the worts are ready for the purpose of fermentation, but that degree varies for different drinks, and in different seasons. I will endeavor to point out the rules to form a judgment for the heat of small beer worts. A greater precision, both for that and for other drinks, will be found in the following table. In July and August, no other rule can be given than that the worts be got as cold as possible. The same rule holds good in June and September, except the season is unnaturally cold. In May and October, worts should be let down nearly 30 degrees colder than the hand. In April, November, and March, the worts should be about 20 degrees colder than the hand, and only 10 in January, February, and December. It may perhaps be thought that the heats here specified are great, but worts cool as they run from the backs to the working tuns. They are also affected by the coldness of the tuns themselves, and perhaps these circumstances are not so trivial, but that an allowance should be made for them. In general, the heat of no must should exceed 60 degrees, because fermentation increases this or any other degree, in proportion to that, under which this particular part of the process begins. To render the thermometer more useful, and to suit it to our conveniency, we have before supposed every first mash for common small beer to be made at 4 o'clock in the morning. In this case, and where the worts are not laid to cool at more than 1 inch in depth, the following table may be said to be a measure of time. The first and last worts for this drink should be let down at a table. Shewing nearly the times the first and last worts of common small beers should be let down in the working tuns, supposing the first mash of the brewing to be made at 4 o'clock in the morning, and no uncommon change happens in the heat of the air. Air 30, first wort 3 o'clock, second wort 5 o'clock. Air 35, first wort 3½ o'clock, second wort 6½ o'clock. Air 40, first wort 4 3/4 o'clock, second wort 8 o'clock. Air 45, first wort 4 3/4 o'clock, second wort 9 1/4 o'clock. Air 50, first wort 5 1/2 o'clock, second wort 11 1/2 o'clock. Air 55, first wort 6 1/2 o'clock, second wort 1 1/2 o'clock. Air 60, first wort 7 1/2 o'clock, second wort 2 1/2 o'clock. Air 65, first wort 8 o'clock, second wort 2 1/2 o'clock. Air 70, first wort 8 1/2 o'clock, second wort 3 o'clock. Air 75, first wort 9 o'clock, second wort 3 o'clock. Air 80, first wort 9 o'clock, second wort 4 o'clock. Small beer worts being nearly alike in consistency, the necessary variations from this table must be less frequent. It is true, some difference may happen from the exposition of a brewhouse, or from other circumstances, admitting more or less freely the intercourse of the air, and be such as might alter, upon the whole, the time set down in the preceding page. Brown beer worts, which are more thick and glutinous, and especially amber worts, which are stronger still, will require other and longer terms to come to their due temperature, to be fermented at. But when once observed and noted, according to various degrees of heat in the air, at 8 o'clock each morning, the conveniency of these observations must be such, in this business, which requires long watchings and attendance, that no arguments are necessary to recommend what is rather indulgence than industry. A table, shewing the degrees of heat worts should be at, to be let down from the coolers into the working tuns, according to the several degrees of heat in the air. Heat of the air 25, common small 75, all keeping beers 59, amber or ales 55. Heat of the air 30, common small 70, all keeping beers 56, amber or ales 54. Heat of the air 35, common small 65, all keeping beers 53, amber or ales 53. Heat of the air 40, common small 60, all keeping beers 50, amber or ales 52. Heat of the air 45, common small 55, all keeping beers 50, amber or ales 51. Heat of the air 50, common small 50, all keeping beers 50, amber or ales 50. 55 and 60 heat of the air. In these cases, when the medium heat of the air is greater than that which the worts should ferment, bring them as near as possible to their temperature. It has been observed that the coldest part of the natural day is about 1 hour before sun rising. The consequences of worts being set to ferment in an undue heat, are the following. In strong beers, or such as are intended for long keeping, if the worts are too cold, a longer time is required for their fermentation, and the drinks grow fine with more difficulty. If, on the contrary, they are too hot, acidity, and a waste of some of the spirituous parts must ensue. Either of these disadvantages appears more conspicuous in common small beer, as, in winter, this drink is seldom kept a sufficient time to correct the defect, and in summer, from being too hot, it becomes putrid, or, in the terms of the brewery, is hereby foxed. End of section 30. Section 31 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 31. Of yeast, its nature and contents, and of the manner and quantities in which it is to be added to the worts. Musts, or worts, though ever so rich, when unfermented, yield no spirit by distillation, nor inebriate, if drank in any quantity. The oils, as yet not sufficiently attenuated for this purpose, become so only by fermentation. Air is absolutely necessary for this process, in the course of which, some of the aerial parts mixing with, and being enveloped by, oils greatly thinned, are enclosed in vesicles not sufficiently strong to resist the force of elasticity, or prevent a bursting and explosion. In the progress of the act, the air joins with oils both coarser and charged with earthy particles. A coat is formed capable of resisting its expansion, and if the bubbles cannot come to a volume sufficient to be floated in and upon the liquor, they sink to the bottom, and take the appellation of lees of wine. Between these two extremes, there is another case, when the bubbles are sufficiently strong to hold the air, but not weighty enough to sink. After floating in, they emerge, and are buoyed upon the surface of the liquor, and there remaining entire, are termed the flowers of wine. Both lees and flowers are, therefore, vesicles formed out of the must, filled with elastic air, and, either separately or when mixed together, they obtain the general denomination of yeast. We have often mentioned the power of fire in driving the air out of worts. Yeast, fraught with the principle now wanted for fermentation, is, therefore, the properest subject to be added to the must, but its texture is various, in proportion to the different heats of the extracts it was formed from. Keeping drinks, extracted with hotter waters, yield yeast, the oils of which have a greater spicitude. It is consequently slower, more certain, and most fit to promote a cool and gentle fermentation. That, on the contrary, which is produced from small beer, being weak, and acting at once, is apt to excite a motion like that of effervescence. Such yeast ought, therefore, not be used, but when there is no possibility to obtain the other. The longer wines or beers are under the first act of fermentation. The greater variety will be found in the texture of the bubbles, which compose their flour and lees. Wines made out of grapes, in general, require a time somewhat longer than the worts of malt, before this first period is at an end, and we have seen that in them fermentation first brings forth air bubbles, whose constituent parts are most tender, and afterwards some that are of a stronger texture. As malt liquors require a less time to ferment, their bubbles are more similar. On this account, the whole quantity of yeast necessary to a wort should not be applied at once, lest the air bladders, bursting nearly in the same time, should prevent that gradual action, which seems to be the aim of nature in all her operations. Keeping beers, formed from low-dried malts, occasion the greatest variety of heat in the extracts, and from hence these musts form yeast, whose bubbles differ most in magnitude and strength. A drink, then, properly made from pale malt, nearly resembles natural wines, especially when they are so brewed as to require precipitation to become transparent. Cleansing is dividing the drink into several casks. This checks the motion occasioned by fermentation, and consequently retards it. To prevent this from being too sensibly felt, some yeast should be put to the drink before it is removed into the casks, as the constituent parts in strong beers are more tenacious than in small, and require a greater motion to entertain the fermentation. The drinks, before they be thus divided, should, besides the addition of the yeast, be well roused with a scoop, or by some other means, for 1 hour. This not only blends all the parts together, but attenuates and heats the liquor, and makes it more ready to begin to ferment again, when in the casks. 1/6 part of the whole of the yeast used is generally reserved for this purpose, and the remainder is equally divided as the worts are let down. It must be observed that this stirring, though as necessary to small as to strong drinks, is only to be continued for a space of time proportioned to their strength. We have before seen, when a grist of malt is entirely extracted to form common small beer, soon to be expended, 1 gallon of yeast to 8 bushels of grain affords a sufficient supply of air to perfect the fermentation. This takes place when the heat of the air is at 40 degrees, but at the highest fermentable degree, experience shews that half that quantity is as much as is necessary. For some ales, the whole virtue of the malt is not extracted, and what remains is appropriated to the making of small beer. The quantity of yeast used for these drinks must be only in proportion to the strength extracted. From these premises, the following tables have been formed, exhibiting the quantity of yeast proper for the several sorts of drinks, at the different heats of the air. A table, shewing the quantities of yeast necessary for common small beer in every season. Heat of the air, 35 pints of yeast to 1/4 of malt, 9. Heat of the air, 40 pints of yeast to 1/4 of malt, 8. The whole quantity of yeast to be put into the first wort. Heat of the air, 45 pints of yeast to 1/4 of malt, 8. The whole quantity of yeast to be put into the first wort. Heat of the air, 50 pints of yeast to 1/4 of malt, 7. Heat of the air, 55 pints of the yeast to 1/4 of malt, 7. Heat of the air, 60 pints of yeast to 1/4 of malt, 6. The first wort to have 3/4, the second wort to have 1/4. Heat of the air, 65 pints of yeast to 1/4 of malt, 6. Heat of the air, 70 pints of yeast to 1/4 of malt, 5. Heat of the air, 75 pints of yeast to 1/4 of malt, 5. Heat of air, 80 pints of yeast to 1/4 of malt, 4. The first worth to have 1/2 of the whole quantity, the second worth to have the remainder. A table, shewing the quantities of yeast necessary for all keeping drinks, both brown and pale, small and strong. Heat of the worts, 30 pints of yeast to 1/4 of malt, 6. Heat of the worts, 35 pints of yeast to 1/4 of malt, 6. Heat of the worts, 40 pints of yeast to 1/4 of malt, 6. Heat of the worts, 45 pints of yeast to 1/4 of malt, 6. Heat of the worts, 50 pints of yeast to 1/4 of malt, 6. Heat of the worts, 55 pints of yeast to 1/4 of malt, 5. Heat of the worts, 60 pints of yeast to 1/4 of malt, 5. Heat of the worts, 65 pints of yeast to 1/4 of malt, 4. Heat of the worts, 70 pints of yeast to 1/4 of malt, 4. Heat of the worts, 75 pints of yeast to 1/4 of malt, 3. Heat of the worts, 80 pints of yeast to 1/4 of malt, 3. A table, shewing the quantities of yeast necessary for amber and all sorts of ales, after which small beer is made. Heat of the air, 30 pints of yeast to 1/4 of malt, 7 1/2. Heat of the air, 35 pints of yeast to 1/4 of malt, 7. Heat of the air, 40 pints of yeast to 1/4 of malt 7, heat of the air 45, pints of yeast to 1/4 of malt 6 1/2, heat of the air 50, pints of yeast to 1/4 of malt 6, heat of the air 55, pints of yeast to 1/4 of malt 5 1/2, heat of the air 60, pints of yeast to 1/4 of malt 5, heat of the air 65, pints of yeast to 1/4 of malt 4 1/2, heat of the air 70, pints of yeast to 1/4 of malt 4, heat of the air 75, pints of yeast to 1/4 of malt 3 1/2, heat of the air 80, pints of yeast to 1/4 of malt 3. This table is founded on the supposition that the virtue or strength extracted from 1/4 of malt for amber is equal to 5/6 of the whole. In every heat of the air, the quantity of yeast to be used for common small beer made after ale must be 1/5 part of the quantity which the ale required. The additional strength obtained from reboiling the hops requiring further proportion. If, for keeping small beer, nearly in the proportion of 6 pints of yeast to 5 barrels of beer, this will be found to correspond with the rule delivered in the foregoing table. End of section 31. Section 32 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 32 of Practical Fermentation and the Management of the Several Sorts of Malt Liquors, to the period at which they are to be cleansed or put into the casks. The laws of fermentation are universal and uniform, and when it proceeds regularly, its different periods are known by the different appearances of the fermenting liquor. As a particular appellation is given to each of these, it may not be unnecessary here to describe them. 1. The first sign of a wort fermenting is a fine white line, composed of very small air bubbles, attached to the sides of the tun. The wort is then said to have taken yeast. 2. When these air bubbles are extended over the whole surface of the must, it is said to be creamed over. 3. Bubbles continuing to rise, a thin crust is formed, but as the fermentation advances rather faster near the sides of the tun than in the middle, this crust is continually repelled, from which arises the denomination of the wort parting from the tun side. 4. When the surface becomes uneven, as if it were rock work, this stage of fermentation, which has no particular use, is distinguished by its height. 5. When the head becomes lighter, more open, more uniform, and of a greater depth, being round or higher in the middle than in any other part, and seeming to have a tendency still to rise, the liquor is denominated to be of so many inches. Head not fit to cleanse. 6. This head having risen to its greatest height, begins to sink, to become hollow in the middle, and, at the same time, more solid, the colors changing to a stronger yellow or brown. The wort is then said to be fit to cleanse. After this, no farther distinctions are made. If the fermentation is suffered to proceed in the tun, the head continues to sink, and the liquor is often injured. As the denominations and tastes of liquors brewed from malt are numerous, it is impossible to specify each separate one. We shall therefore only particularize such sorts of drinks as were taken notice of in the section of extraction, they being most in use. But, from what will be said concerning them, the method of managing any other malt liquor may easily be deduced. Spontaneous pellucidity arises from a due proportion of the oils to the salts in the worts, But the advantage of long keeping depends not only on the quantity of oils and hops the musts possess, but also on the fermentation being carried on in a slow and cool manner. All drinks intended long to be kept are therefore best formed in cold weather, and made to receive their yeast at such temperature as is set forth in the table. The yeast is to be divided in proportion to the quantities of wort let down, until the whole, being mixed together, receives its allotted portion, except so much as is to be put in just before cleansing. Under these circumstances, drinks, which are brewed for keeping, are suffered to go through the first process of fermentation, till they are so attenuated that the liquor becomes light, and the head, or the yeast, laying on the surface of the beer, begins to sink. When, or somewhat before, this head has fallen to nearly half the greatest height it reached to, a remarkable vinous smell is perceived, and the liquor, at this term, is to be put into casks, being first well roused with the remaining part of the yeast, in the manner mentioned in the preceding section. By the description given of the origin of yeast, it appears that it is formed rather of the coarser oils of the worts. If the cleansing is not done when the head is sunk down to half the greatest height it rose to, by falling lower, some part of these coarser oils return into the beer, then under fermentation, and gives it a flat, greasy taste, technically termed yeast bitten. When, on the contrary, beers or ales are removed too soon from the first tumultuous fermentation, for want of having been sufficiently attenuated, and from not having deposited their lees, nor thrown up in flowers their coarser oils, they are less vinous than otherwise they would have been, appear heavy, ale, and are said not to have their body sufficiently opened. The fermentation of common small beer is, through necessity, carried on so hastily that it is hardly possible to wait for the signs which direct the cleansing of other beers. This drink being generally brewed and fermented within 24 hours, its state, with regard to fermentation, is best judged of by the quantity of its froth or head at the time of cleansing, which, in proportion to the heat of the air, may be determined by the following table. A table shewing the depth of head which common small beer should have to be properly cleansed in every season of the year. Heat of the air 25 degrees, head of the beer in the tun 6 inches. Heat of the air 30 degrees, head on the beer in the tun 5 inches. Heat of the air 35 degrees, head on the beer in the tun 4 1/4 inches. Heat of the air 40 degrees, head on the beer in the tun 3 1/2 inches. Heat of the air 45 degrees, head on the beer in the tun 2 3/4 inches. Heat of the air 50 degrees, head on the beer in the tun 2 inches. Heat of the air 55 degrees, head on the beer in the tun 1 1/2 inches. Heat of the air 60 degrees, head on the beer in the tun 1 inch. Heat of the air 65 degrees, head on the beer in the tun 3/4 inch. Heat of the air 70 degrees, head on the beer in the tun 1/2 inch. Heat of the air 75 degrees, head on the beer in the tun 1/4 inch. Heat of the air 80 degrees, head on the beer in the tun just taken. As it is chiefly by the action of the air that wines are formed, if we contrive to shift this powerful agent on the surface of a must under fermentation, and to convey it more forcibly and hastily into the wort, its efficacy will be renewed, the fermentation accelerated, the liquor quickly become transparent, and soon be brought to the state of maturity age might slowly make it arrive at. Amber or pale ales require the hottest extracts pellucity admits of to be made strong, and at the same time soft and smooth to the palate. But, as ales do not admit of any large quantity of hops, which would alter their nature, there is a necessity to perform hastily the act of fermentation, and to carry it on to a higher degree that is common in other malt drinks. The method of exciting and conducting repeated fermentations, with success, is perhaps not only the most difficult, but the most curious, part of the process. I shall therefore conclude, with an account of it, what I have to say with regard to the practice of fermentation, the amber wort being let down, as its proper degree of heat, into the fermenting tun, out of the whole quantity of yeast allowed for this drink. In the table, page 317, 1/7 part must be kept to be used, as hereafter shall be mentioned. Suppose the heat of the air is at 40 degrees, and 8 quarters of malt have been brewed for this purpose. The whole of the yeast required is 7 gallons, from which 1 is to be reserved. Of the 6 remaining gallons, 1/2, or 3, are to be put to the wort of its first coming down, when the whole must be well roused, or mixed, thoroughly to disperse the enlivening principle the yeast conveys, hereby to prevent putrefaction, or foxing in any part. And of the last 3 gallons, about 3 quarts must be added to the drink, every 12 hours, until it ferments to the highest pitch of the period mentioned in Article 5, page 319. This successive putting in of yeast is called feeding the drink. Before and about the time the head is got to this height, all the dirt or foul yeast that rises on the surface must be carefully skimmed off. It is easily distinguished from the pure white froth by its color, and by the sinking of the head occasioned by its weight. Length of time might attenuate some of these coarser oils in a less artificial fermentation, but as this help is not to be waited for, and every obstacle to pellucity must be removed, the brewer's attention to this point cannot be too great. The head of the drink having reached its utmost height, the reserved gallon of yeast is to be used, in order to give to the ale a sufficient power to bear the repeated fermentations it is to undergo, by being beat in, every 2 hours, with a jet or scoop, for 1/4 of an hour, so that the head of the drink is each time to be reduced to the least height it is capable of. This striking in being continued, the drink will periodically require it, and be damaged if it be neglected. After it has undergone more or less of these fermentations, in proportion to the heats of the worts and of the air, the brewer is carefully to observe, when the head ceases to rise to its accustomed height, and then to examine the drink, by having the jet filled with it at the bottom, and brought through the whole body to the top, a small part of which being poured in a hand gatherer, he will see whether the lees form themselves in large white flakes, and readily subside, and be informed, by the taste, whether the sweet of the wort is gone off, and the ale become vinous. If these 2 circumstances concur, the drink is to be beat in with the jet as before, but not roused as porter or other beers are, for the lees, which in this drink are in greater quantity, would, by this management, so intimately be mixed with it, as with difficulty to separate themselves again, if at all. It is then time to cleanse it, but the casks, at all times, more especially in summer, must be well filled up with clean drink, that is, part of the very drink which was cleansed, avoiding that produced in the stillings, as this, for want of standing a sufficient time, is always yeasty, and the yeast, being greatly attenuated by the working of the drink, easily dissolves in the ale, and renders it foul and ill-tasted. As the right forming of amber ales is looked upon to be the highest pitch of the art of pale beer brewing, I have dwelt longer on this article than otherwise it might seem necessary, to shew the connection there is between every sort of malt liquors, but it should be observed, the same method of fermenting it is to be practised both winter and summer, varying only the quantities of yeast in proportion to the season, for where, in winter time, this drink is fed with 3 quarts of yeast every 12 hours, half a gallon will answer the same intent in summer. Upon the whole, the process is contrived to accelerate fermentation, yet, the more coolly and gently it is performed, the better will the ales be. I have before hinted, if Madeira wines were fermented in this manner, they would sooner become fit for use, more especially as they need no ferment to excite them. However, this method of forming drink to be soon fit for use, has, either through interest or prejudice, been taxed with being unwholesome, but upon what grounds, I must confess I could never yet discover, as no reason of any moment has ever been alleged for this assertion. Section 32. Section 33 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 33 of the Signs generally directing the processes of brewing and their comparison with the foregoing theory and practice. We have now brought our barley wines into the casks, and this on principles, it is thought, agreeable and consonant to each other, as the charge of novelty may be alleged, to invalidate what has been offered. It is but just to pay so much regard to a long, and, upon the whole, successful practice, as to recite, if not all, at least the principal maxims and signs in brewing, which hitherto have guided the artist. By comparing these with the present method, they will not only illustrate each other, but perhaps cause both to be better understood. And though, with respect to the art itself, this may be thought rather a curious than an instructive part, yet we may learn, from hints, that such practice, which long experience has proved to be right, will always correspond with true theory. 1. When a white flour settles, either in the underback or copperback, which sometimes is the case of a first extract, it is a sure sign such an extract has not been made sufficiently hot, or, in technical terms, that the liquor has been taken too slack. Malt, when dried, has its oils made tenacious, in proportion to the power of heat it has been affected with. The grain, though ground, if the water for the extraction is not at least as hot as what occasioned this tenaciousness, must remain in great measure undissolved in the first extract, and deposit itself as just now was mentioned. 2. The first extract should always have some froth or head in the underback. The oils and salts of the malt, being duly mixed, form a saponaceous body, the character of which is that, on being shook, it bears a froth on its surface. 3. The head or froth in the underback appearing red, blue, purple, or fiery, shews the liquors to have been taken too hot. The hotter the water is, when applied to the malt, the more must the extract abound with oils, and consequently be more capable to reflect colors in a strong manner. But how precarious this method of estimating the quality of an extract is, in comparison to that which the thermometer affords, will appear from the following observation of Sir Isaac Newton. Saponaceous bubbles will, for a while, appear tinged with a variety of colors, which are agitated by the external air, and those bubbles continue until such time as, growing excessive thin, by the water trickling down their sides, and being no longer able to retain the enclosed air, they burst. Now as these bubbles vary in their density in proportion to their duration, the colors they reflect must continually change, and therefore it is not possible to form an accurate judgment of the condition and saponaciousness of the extracts, by the appearance of their froth, for, when the grist feels slippery, it generally is a sign that the liquors have been taken too high. This appearance proceeds from an over quantity of oil being extracted, and is the effect of too much heat. 5. Beer ought always to work kind out of the cask when cleansed, but the froth, in summer, will be somewhat more open than in winter. The higher and hotter the extracting water is, the more oils doth it force into the must. When a wort is full charged with oils, the fermentation is neither so strong nor so speedy, and consequently the froth, especially the first, is thin, open, and weak. This improves as the liquor is more attenuated, and heat, which expands all bodies, must rarefy the yeasty vesicles, the principal part of which is elastic air. But this open head, even in the summer-time, improves to one more kind, as the first, the most active period of fermentation, draws nearer to its conclusion. However vague and indeterminate these signs are, it would not be impossible to bring them to some degree of precision, but, upon the whole, this method would increase our difficulties, and yet, as to certitude, be inferior to the rules we have endeavored to establish. We think it unnecessary to pursue any farther a research most likely neither entertaining nor useful. End of section 33. Section 34 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 34. An inquiry into what may be, at all times, a proper stock of beer, and the management of it in the cellars. The business of a brewer is not confined to the mere manufacture of his commodity. His concerns, as a trader, deserve no less regard, and, in a treatise like this, should not be entirely omitted. As it is a fault not to have a sufficient stock of beers in the cellars to serve the customers, it is one also to have more than is needful. By the first of these errors, the beers would be generally new and ill disposed for precipitation. By the other, quantities of stale beer must remain, which, becoming hard, will at last turn stale, and be unfit for use, unless blended with new brewed beers, to their detriment. These faults, if continued, may in time affect a whole trade, and ought therefore carefully to be avoided. For these reasons, the whole quantity to be moved, or expected to be supplied from the brewer's store cellars, during the space of 1 12-month, should be calculated, as near as possible. Half this quantity ought to be the stock kept up from November to May inclusive, and nearly 1/3 part thereof be remaining in September. From hence a table may be formed, by which it will be easy, at one view, to know the quantity that should be maintained at every season of the year, and to avoid almost every inconveniency which otherwise must arise. Suppose, for example, the number of casks expected to be moved in a year to be 320 butts and 248 puncheons. The store cellars ought to be supplied, as to time and quantity, in the following proportion: January, butts 160, puncheons 124, February, butts 160, puncheons 124, March, butts 160, puncheons 124, April, butts 160, puncheons 124, May, butts 160, puncheons 124, June, butts 146, Puncheons 113, July, butts 133, Puncheons 103, August, butts 120, Puncheons 93, September, butts 107, Puncheons 82, October, butts 133, Puncheons 103, November, butts 160, Puncheons 124, December, butts 160, Puncheons 124. After beers have been started in the cellars, the casks should be well and carefully stopped down, as soon as the repelling force of fermentation is so much lessened as not to be able to oppose this design. Otherwise the elastic air, which is the vivifying principle of the drink, being lost, it would become vapid and flat, and if left a long time in this condition, perhaps grow sour. It has already been observed that cellars, in winter, are more hot than the exterior air by 10 degrees, and more cold in summer by 5 degrees. But besides this general difference, repositories of beer vary surprisingly in their temperature, from the nature of the soil in which they are built, from their exposition to the sun, or from other incidental causes. As heat is a very powerful agent in accelerating fermentation, it is by no means surprising, not only that some cellars do ripen drinks much sooner than others, but also that a difference is often perceived in the same cellar. The persons entrusted with the choice of beers, with which the customers are to be served, should not be satisfied to send out their guiles in the progressive order in which they were brewed, but ought, on every occasion, to note any alteration that happens in the drink, as this is doing justice both to the commodity and to the consumer, who has a constant right to expect his beer in due order. End of section 34.
Section 35 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 35 of Precipitation and Other Remedies applicable to the diseases incident to beers. No accident can be so detrimental as leaky or stinky casks, whose loose or spoil the whole or part of the contained drink. The necessity of having on these occasions a remedy at hand was undoubtedly the reason why coopers were first introduced in store cellars. Constant practice might have qualified their palates so as to make them competent judges of the tastes of wines and beers, and to enable them to know which were the fittest for immediate use. The preparing or forcing them for this service was a matter which the prophet gained and thereby made them ready enough to undertake. Chemists, whom they consulted on this occasion, gave them some informations, from whence the coopers became the possessors of a few nostrums, the effects of which they were supposed to have experienced, but ignorant of the causes of most, if not all the defects they undertake to remedy, and unacquainted with the constituent parts of beers, it is not to be expected that their success should be constant and uniform. The brewer, earnest to his duty, and to excel, ought to keep a particular account of every brewing. By this means he best can tell how he formed the drink, and ought consequentially, in any disorder, to be prepared to direct the properest remedy. The intent of this treatise has been to discover the means by which errors may be avoided. Chemical applications are intended to remedy those errors, which may be occasioned either by carelessness or accident. The wholesomeness or propriety of those applications, which will be indicated, must be left to the judgment of my readers. it is most likely that there is sufficient room for improvement, and we might expect it from those whose profession it is to study everything that may be conducive to the safety of mankind. Whatever vegetable wines are produced from, whenever they deviate from their respective perfection, a well-conducted fermentation might have made them arrive at, they may be said to be distempered. Foulness, or want of transparency, is not the least evil, but, according to its degree, it obtains various appellations and requires different helps. From what has been said, nothing can be more plain than that it is always in our power to form beers and ales which will be bright. Yet porter or brown beer is constantly so brewed as to need precipitation. The reasons for this management have before been offered. Were we to wait till the liquor became transparent by age, a more real disorder would ensue, that of acidity. Precipitation is then serviceable, especially when beers are to be removed from one cellar to another, a short space of time before they are to be used. By being shook, and the lees mixed with the liquor, a strong acid taste is conveyed therein, and the power of subsiding, which is wanted, renders the forcing them in that case of absolute necessity. In beers brewed with liquors sufficiently heated, no flatness is occasioned thereby, as in the case, under like circumstances, with liquors produced by low extracts, from grain not sufficiently dried. The degree of foulness in porter should, however, be limited. Its bounds ought not to exceed the power of 1 gallon of dissolved isinglass to a butt. Isinglass is dissolved in stale beer and strained through a sieve, so as to be the constance of a jelly. The beer is set in motion with a stick, which reaches 1/3 part down the cask before and after this jelly is put in, and a few hours should be sufficient to obtain the desired effect. We have observed that this quantity of jelly of isinglass is equal to a medium of 10 degrees dryness in the malt and heat of the extracts. When the opacity exceeds this, the liquor is termed stubborn. The same quantity of dissolved isinglass, repeated, is often sufficient. If not, 6 ounces of the oil of vitriol are mixed in. An effervescence is, by this addition, produced. The oils of the drink become more attenuated, and the weight added to the precipitating matter is a means to render it more efficacious. Instead of the oil of vitriol, 6 or 8 ounces of the concrete of vitriol, pounded and mixed with the isinglass, are sometimes used with success. A foulness in beer beyond that which is called stubborn gives to the drink the denomination of gray beer. This arises from the oils which float upon the surface, and which the liquor has not been able to absorb. In this case, the same methods as before mentioned are repeated. The quantity of dissolved isinglass is often increased to 3 gallons, that of vitriol to more than 12 ounces, and sometimes a small quantity of aqua fortis is added to these ingredients. The next stage of opacity is cloudiness, when the cooper confesses that the distemper exceeds the power of his menstruums, and that his attempts extend no farther than to hide the evil turnsoil and cochineal, were they not so expensive, might in this case be used with success. But what is less known, and would greatly answer the intent of hiding the dusky color of the drink, is madder. About 3 or 4 ounces of this is the proper quantity for a butt of beer. Calcined treacle, by the coopers called blacking, from its acidity is of some small service, for, by coloring the drink, it somewhat lessens the gray hue thereon. A quart is generally used in a butt, And to prevent the defect in the beer being noticed by the consumer, the practice is to put thereon what is called a good cauliflowered head. This might be done by using as much pounded salt of steel as will lay upon a shilling. But the difference in price between this salt and copperas makes the last generally to be preferred. The strong froth on the top of the pot, which that foams about it, together with somewhat of a yellow cast, are often mistaken for the signs of a superior merit and strength, though in fact they are those of deceit. A little reflection that the natural froth of beer cannot be yellow, nor continue a long time, especially if the liquor has some age, would soon cure mankind of this prejudice. Cloudy beers, under these circumstances, though not cured, are generally consumed. Beers become sick from their having so large a portion of oils as to prevent the free admission of the external air into them. The want of this enlivening element makes them appear flat, though not vapid. Such beer should not, if possible, be brought immediately into use, as age alone would effect their cure. But when this cannot be complied with, every means that will put the beer upon the fret, or under a new fermentation, must be of service. By pitching a butt head over head, the lees of the beer, which contains a large proportion of air, being mixed again with the drink, help to bring on this action and to remove the sickness. Burnt hash thorn shavings, to the quantity of 2 pennyworth, put into a butt, are often of use. Balls made with 8 ounces of the finest flour and kneaded with treacle convey likewise air to the drink and promote its briskness. Beers, by long standing, often acquire so powerful an acid as to become disagreeable. The means of correcting this defect is by alkaline or testaceous substances, and in general by all those which have the property of absorbing acids. To a butt of beer in this condition, from 4 to 8 ounces of calciline powder of oyster shells may be put, or from 6 to 8 ounces of salt of wormwood. Sometimes a pennyworth or 2 of whitting is used, and often 20 or 30 stones of unslacked lime. These are better put in separately than mixed with the isinglass. From 2 to 6 pounds of treacle used to 1 butt of beer has a very powerful effect, not only to give a sweet fullness in the mouth, but to remove the acidity of the drink. Treacle is the refused sweet of the sugar baker, part of the large quantities of lime used in refining sugars, undoubtedly entered in its composition, and is the occasion of its softening beers. In proportion as beers are more or less forward, from 2 to 4 ounces of salt of wormwood and salt of tartar, together with 1 ounce of pounded ginger, are successfully employed. All these substances absorb acids, but they leave a flatness in the liquor, which in some measure is removed by the use of ginger. Sometimes in summer, when beer is wanted for use, we find it on the fret. As it is then in repelling a state, it does not give way to the finings, so as to precipitate. For this, about 2 ounces of cream of tartar mixed with the isinglass, and if not sufficient, 4 ounces of oil of vitriol are added to the finings next used, in order to quiet the drink. Some coopers attempt to extend their art so far as to add strength to malt liquors, but let it be remembered that the principal constituent parts of beer should be malt and hops. When strength is given to the liquor by any other means, its nature is altered, and then it is not beer we drink. Treacle in large quantities, the berries of the Coccosus indicus, the grains of paradise, or the Indian ginger pounded fine, and mixed with a precipitating substance, are said to produce this extraordinary strength. It would be well if the attempts made to render beer strong by other means than by hops and malt were to be imputed to none but coopers. Cocculus indicus, and such like ingredients, have been known to be boiled in worts by brewers who are more ambitious to excel the rest of the trade than to do justice to the consumers. Were it not that pointing out a vice is often the means to forward the practice of it, I could add to this infamous catalog more ingredients. It were to be wished practitioners never knew either the name or nature of for fining, softening, and strengthening. Formerly brown beers were required to be of a very dark brown, inclinable to black. As this color could not be procured by malt properly dried, the juice of the elderberries was frequently mixed with the isinglass. This juice afterwards gave way to calcinine sugar. Both are needless, as time and knowledge remove our prejudices, when the malt and hops have been properly chosen and applied to their intended purpose. Such are the remedies cheaply made use of for brown beers. Drinks formed from pale malt are always supposed to become spontaneously fine, and when they are so, by being bottled, they are saved from any farther hazard. It is impossible for any fermented liquor to be absolutely at rest. The reason of beers being preserved by this method is, thereby, they are depraved of a communication with the air and, without risk, gain all the advantages which age, by slow degrees, procures, and which art can never imitate. Were we as curious in our ales and beers as we are in the liquors we import? Did we give to the produce of our own country the same care and attendance which we bestow on foreign wines? We might enjoy them in a perfection at present scarcely known, and perhaps cause foreigners to give to our beers a preference to their own growth. End of section 35, recorded by Matthew Newell.
Section 36 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Theory and Practice of Brewing by Michael COMBRUNE. Section 36 of Taste. Dr. Grew, who has treated of this matter, divides taste into simple and compound. He mentions the different species of the first, and calculates the various combinations of the latter, the number of which exceeds what at first might be expected. Without entering into this detail, I think that the different tastes residing in the barleys, or formed by their being malted and brewed with hops, may be reduced to the following: the acid, which is a simple taste; the sweet, which is an acid smoothed with oils; the aromatic, which is a compound of a spirituous acid and a volatile sulfur; the bitter, which, according to our author, is produced by an oil well impregnated either with an alkaline or an acid salt shackled with earth; the austere, which is both astringent and bitter; and lastly, the nauseous and rank, which is, at least in part, sometimes found in beers which have either been greatly affected by fire, or by long age have lost their volatile sulfurs, and have nothing left but the thicker and coarser oils, resembling the empyreumatic dregs of distilled liquors not carefully drawn. The number of circumstances on which the taste of fermented liquors depends are so various, that perhaps there never were any two brewings, or any two vintages, which produced drinks exactly similar. But as, in this case as well as in many others, the varieties may be reduced under some general classes, the better to distinguish them, let us inquire which taste belongs to different malt liquors, according to the several circumstances in which they are brewed. In beers and ales, the acid prevails in proportion as the malt has been less dried, and heat was wanting in the extracting water. The sweet will be the effect of a balance preserved between the acids and the oils. When, by the means of hotter waters, oils more tenacious are extracted from the grain, whereby the more volatile sulfur is retained, the taste becomes higher in relish or aromatic. If the heat is still increased, the acids, and the most volatile oils, will in part be dissipated, and in part be so enveloped with stronger oils as the bitter of the hops appears more distinct. A greater degree of fire will impress the liquor with an austere, rough, or harsh taste, and a heat beyond this so affects the oils of the grain as to cause the extracts to be nauseous to the palate. Besides these, there may be other causes which produce some variation in taste, as a superior dryness in the hops, an irregularity in the ordering of the heat of the extract, too great an impetuosity or slowness in the fermentation, the difference of seasons in which the drink is kept. But as these causes affect the liquor in a low degree in comparison with the drying and extracting heats of the grain, and inquiring into their consequences is not absolutely material. Beers or ales, formed of pale malt, in which a greater portion of the acids is contained, with less tenacious oils, are not only more proper to allay thirst, but in general more aromatic than brown drinks. The oils of these last, being by the effect of fire rendered more compact, and more tenacious of the terrestrial parts raised with them, are attended with something of an austere and rank taste. This seems to be the reason why brown beers require more time, after they have been fermented, to come to their perfection. The air, by degrees, softens and attenuates their oils, and by causing the heterogeneous particles to subside, makes them at last, unless jarring heats have been used, pleasing to the palate, whereas they were before austere, rank, and perhaps nauseous. By means of the thermometer, we have endeavored to fix the different colors of malt, the duration of the principal sorts of drink, and the tendency each has to become transparent. The same instrument cannot probably have the same use when applied to distinguish the different tastes, as these depend on a variety of causes not easy to be ascertained. Yet something of this nature may be attempted upon the following principles. As the chief circumstance which produces a variety of tastes in malt liquors is fire or heat acting on the malt and hops, and the effect of the air, put in motion by the same element, the table here subjoined may point out what tastes are in general occasioned by the combination of these two causes. A table determining the tastes of malt liquors. Heat of air, dryness and extracting heat, predominant taste. 80° heat of the air, 119° dryness and extracting heat, predominant taste, acid. 76, 124, acid sweet. 73, 129, acid sweet. 70, 134, acid sweet bitter. 66° heat of air, 138 dryness and extracting heat, sweet bitter. 63, 143, sweet bitter. 60, 148, bitter aromatic. 56, 152, bitter aromatic. 53, 157, bitter aromatic austere. 50° heat of the air, 162° dryness and extracting heat, aromatic austere. 46, 167, austere, nauseous. 43, 171, austere, nauseous. 40, 176, nauseous. The first column of the table shows the fermentable degrees reversed. As the hotter the season is, the more fermented drinks tend to acidity, the direct contrary of which is the consequence of an increase in the heat malt or hops are dried and extracted with. The assistance of this table, though small, ought perhaps not to be entirely slighted, as it seems at least to show that the useful is seldom separated from the elegant, and that a medium between extremes is most agreeable both to the operations of nature and the constitution of our organs. The impressions of taste are less in proportion as the drinks are weak. The strongest wine yields the most acid vinegar. Time wears away this acidity much sooner than it doth the nauseousness occasioned by vehement heats. This circumstance shows how necessary it is, in the beginning of the process of brewing, to avoid extracts which are too weak, as from hence, in its conclusion, such would be required whose great heat would render the drink rank and disagreeable. That proportion between the salts and the oils, which constitutes soundness and pellucidity, is most pleasing to the taste, and seems to be the utmost perfection of the art. As the sun never occasions a heat capable of charring the fruits of the vine, we never meet with wines endued with a taste resembling the emporomatic, which we have here represented. This error, being inexcusable in any liquor, ought carefully to be guarded against, and from what has been said, we should learn this important truth, that nature is the best guide, and that, by imitating as near as possible her operations, we shall never be disappointed in our ends. End of section 36. Recording by Todd.
Section 37 of the Theory and Practice of Brewing. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elsie Selwyn. The Theory and Practice of Brewing by COMBRUNE. Section 37. Appendix. Though this work has already been carried to a great length, I hope those of my readers who may have done me the honor to go attentively through the whole of it will pardon me the addition of a few incidental thoughts and queries. The chain of arts is so well connected that researches, originally intended for the illustration of any one of them, can hardly fail of throwing some light upon others. 1. The seed of plants cannot be put in a fitter place for perfect vegetation than when buried underground at a depth sufficient to defend the young shoots from the vicissitudes of heat and cold, and the disadvantage of too much moisture. The manuring of the earth and the steeping the seed into solutions of salts have been found in some cases to increase the strength of the grain, to correct its original defects, and to prevent the noxious impressions of a vicious ground. Plants are made to germinate in water alone, and this experiment, so successfully carried on every winter in warm apartments, may still be improved by dissolving salts in the water. Could the barley used for malting be put in the ground, its growth would be more natural, and its oils become more miscible with water, by the saline nourishment derived from the earth, might yield more vinous, more strong, and more lasting liquors. But as this method is impracticable, would it be impossible to increase the efficacy of that which is used? Consult Home on Agriculture. Might not either nitrate or saltpeter be added to the water with which the grain is moistened? Are they not used with success to manure land? Are not solutions of them in water employed by the farmer to steep his sowing seed? I barely mention these as some of the substances that might be employed in the malting of barley, and am far from thinking there are none other. Perhaps different salts should be used, according to the nature of the soil from which the corn was produced. But a variety of experiments seems to be required in order to discover how far art might in this case imitate and improve nature. A small quantity of malt at all times, but especially when brewed in large vessels, parts too readily with the heat which extraction requires, and on the contrary, if the quantity of malt be very great, the heat may not be uniformly spread. A forward beer inclinable to acidity is often the result of too short a grist. A thick, stubborn, and rank liquor many times is produced from too large a one. Every advantage may be had in brewing properly. 5 or 6 quarters of malt. It is difficult to succeed if the number exceeds 50. 3. The strong, pungent, volatile spirit which exhales from a must when under full fermentation has been supposed to be a loss which might be prevented, and accordingly attempts have been made to retain these flying, impetuous particles by stopping the communication between the atmosphere and the fermenting drink. That there is a dispersion of spirits is beyond doubt, and that these exhaling vapors consist of the finest oils, which the heat forces out of the must, is equally certain. But this loss seems to be abundantly repaid by the stronger oils, which the same degree of heat attenuates and substitutes in a larger quantity to the former. The last oils could never come under the form of a vinous liquor, but by a power which sooner or later dissipates some of the first. Pale ales or amber not only lay for many days exposed to the open air, but suffer, by the periodical renewal of the action of the air, every 2 or 4 hours, a much more considerable loss of spirits than when fermentation is carried on uniformly. Yet experience shows that so many oils are, by this method, attenuated, that the strength acquired greatly surpasses that which is lost. 4. The practice of fermenting by compression recommended to distillers seems on this account less useful than might be concluded from theory alone. The intent of the distiller as well as of the brewer is to extract the greatest quantity of spirituous oils. It is impossible to ferment a must in vacuo. Air is absolutely necessary to carry on this operation, even a superabundant quantity of oils admitted into the must, by obstructing the free admission of the air, impedes fermentation, prevents the wine from reaching pellucidity, and sometimes is the occasion for becoming putrid. 5. When the purest spirit is intended to be drawn from the grain, the fermented wash ought to be suffered to settle till it becomes transparent. The dispatch with which the distillery is generally carried on often prevents this useful circumstance taking place, and occasions a want of vinosity in the liquor. In many cases, the extraordinary charges of extracting the grist from malted corn in the manner which has been directed for drinks intended a short space to be kept, and of suffering the fermented wash to be meliorated by time until it becomes vinous and spontaneously transparent, might be abundantly repaid. Yet, if hurry must be a part of the distiller's business, he should at least make such extractions as admit of the speediest fermentation and the readiest pellucidity. He cannot expect corn spirits to equal the brandies of France, unless his worts are similar to the wines distilled in that kingdom, where those used for this purpose are weak, fine, and tending to acidity. He would therefore secure to himself the greatest probability of success if he employed only malted corn in his grist. This is the best kind, well germinated in a form of saccharine basis, slack dried, and resolved with weak extracts to preserve into the must a proper proportion of vinosity. If he intended this wash to be formed into a pure spirit, it should be allowed time to become transparent. He might regulate his extracts by such heat as have been fixed for common small beer, brewed when the heat of the air is at the lowest fermentable degree, though perhaps heats less than these, when dispatch is required, might better answer his purpose, especially as the length used in the distillery is nearly the same with that which brewers use for the liquor here referred to. With hot waters to attempt to force from the grain more strength or more oils than such as will form a clean, tasteless spirit, is, in the distillery, a real loss and a fundamental error. By too strong heats, more oils are forced into the must than can be converted in spirits, and fermentation being, by this overcharge, in some measure clogged and impeded, a less yield is made, and the liquor obtained of a rank and often emphreumatic taste. 6. Why are the brandies of Spain inferior to those prepared in France? The wines of the last country are the growth of a weaker sun. They contain no more oils than can be assimilated by fermentation, and form a clean, dry, nutty spirit. The Spanish wines, abounding with more oleaginous than acid parts, this overproportion becomes not only useless, but hurtful in the still, and produces the rankness observed in Spanish brandies. The cleanness of the spirit arises in great measure from the weakness of the must, and its vinosity from the less proportion of oils to the salts. This seems to be the reason why the most grateful spirits are produced from wines unable to bear the sea or to be long kept. 7. The native spirits of vegetables, said Boerhaave, are separated by heats between 94 degrees and 212. To obtain the whole of these, the fire must be gradually increased, for superior heat dissipates the spirits raised by an inferior one. Such parts as might be obtained by 100 degrees are lost if the heat applied be much greater. It is true, the parts of vegetables immersed in water cannot so easily be dissipated as if they were in open air, yet by the rarefaction of the liquid a proportional evaporation, however small, must ensue, or the oils raised by a greater heat may so effectually envelop the finer ones as to make them hardly perceptible either to our smell or taste. Thus, though heated water is able to extract all the virtues residing in the vegetables, the different application of the fire will alter not only their proportions but their properties also, when we consider that pure spirit of wine boils at so low a heat as 175 degrees. If the above principles be true, that surely must be the cleanest spirit which is brought over in the slowest and coolest manner, and it is more than probable, if the rules here laid down be put in practice, the grain of England will be found to yield spirits that may vie with the brandies of France, be more pure than those of the Indies, and excel those of Holland. 8. The vinegar maker is equally concerned with the distiller in the brewing process. Vinegar is produced in the last stage of fermentation, when a gross, tartarous, unctuous matter, consisting of the coarser oils extracted either from the grain or the grapes, generally falls to the bottom of the liquor, and no longer prevents its acidity or affects its flavor. Though the best vinegar proceeds either from the strongest wines or beers, this strength consists in the quantity of fermentable principles, and not in that of mere oleaginous parts. By properly adapting the extracting waters, this hurtful impediment may be removed, and the vinegar from malt liquors become as neat and as strong as that which is made from vine. 9. As the acid taste of vinegar is the effect of a continued fermentation, many people have thought it immaterial how speedily the first parts of the operation were carried on. But violent fermentations not only dissipate some of the fine oils, which should be retained in the vinegar, but also cause the must to tend towards putrefaction. Boerhaave, after he has directed a frequent transvasion of the liquor, observes that, whenever the weather or the workhouse is very hot, it is often necessary to fill the half-emptied vessels every 12 hours, not only to procure a supply of acids from the air, but also to cool the wine and check the too violent fermentation, which, arising in the half-full casks, might dissipate the volatile spirits before they are properly secured and entangled by the acid. Hence the liquor might be sour indeed, but at the same time flat, and would never become a sharp and strong vinegar. 10. Application and uses have frequently been found for materials which before were supposed to be of no value. The grains, after the brewer has drawn his worts out of them, are generally used for the feeding of cattle. But I do not know that hops, after boiling, have been employed to any purpose. Is there nothing more left in this vegetable after it has imparted the virtue wanted to the beer? All plants burnt in open air yield alkaline salts, though in a greater or less quantity, according to the quality of the plants. Boerhaave says that those which are austere, acid, or aromatic yield in their ashes a great abundance of salts, and these, being put in a fusion and mixed with flint or sand, run into glass. Hops thrown after decoction in no great quantity on the fire cause the coals to vitrify, or as it is generally termed, to run into clinkers. If, therefore, the remains of the hops were burnt in open air or in a proper furnace, it seems most likely that no inconsiderable quantity of somewhat like pot ashes might be obtained, and this, considering the many ton weight of hops employed in large cities, and thrown away as useless, might become an object of private emolument to the brewer and of public benefit to the kingdom. Finis. End of section 37. End of The Theory and Practice of Brewing by Michael COMBRUNE.